Okay, on to problem number 3. So this is an analog to digital conversion problem. So we'll need some equations and we'll need to remember how we do that process. So for the first part, what is the resolution Q of the quantizer? So Q is the voltage max minus voltage min over 2 to the n. And the idea is we have some number of bits that we're going to label values with. So with 2 bits, we're going to have 0, 0, 0, 1, 1, 0, and 1, 1. And we're really just trying to identify, what voltage range do each of these values represent? And so what are we sort of matching to the original signal when we see that binary number? Because that's really what we're doing here is we're converting an analog value to a digital value. We have limited digital values, so we're understanding what those represent. So the voltage max minus voltage min, that's for this problem going to be the 2 to negative 2, so 2 volts minus negative 2 volts over 2 to the 2, n is 2 for 2-bit quantizer, which means we have 4 volts over 4, so 1 volt range. And so what would happen here is we'd have, potentially, if we label from the bottom up, negative 2 volts to negative 1 volt would be our 0, 0. So anything that falls in that range, negative 1 point, or 0.9999 volts to 0 volts would be a 0, 1, and then 0.000001 volt to 1 volt might be that, and then 1.0001 volt to 2 volts might be our 1, 1 value. This is really just that's what we're trying to establish is the range that we're labeling each bit value with. So part B, what is the maximum frequency that could be input into this analog to digital converter without incurring aliasing noise? So this is a Nyquist problem, or a Nyquist rate problem. So if you see aliasing mentioned, your thoughts should go straight to the Nyquist rate and that sample. So F Nyquist is 2F max, or is greater than or equal to 2F max, where F max is the maximum frequency that we could sample. So if we're going to sample at a 2 megahertz rate, our Nyquist rate is 2 megahertz. And that's just we're setting that rate, so we're sampling at that. We want that to be higher than the Nyquist rate, so we need 2 megahertz to be greater than or equal to 2 F max, which means our F max, the highest rate thing that we can sample, is going to be 1 megahertz. So again, that's just understanding the equation, knowing that Nyquist rate is greater than or equal to 2F max, and so that's what we're trying to do. So on to the analog to digital conversion here, we're going to use some of those things that we just talked about at the top, and we're going to label this, do the analog to digital conversion for at least part of it. So the first thing says circle the sample points on the analog waveform below. So to do that, we need to know how often we are sampling. And so we have F equals 2 megahertz. We need to remember that then T equals 1 over F, which is going to be 1 over 2 times 10 to the 6th. And that's going to give us something like 0.5 microseconds. So we can see our scale here on the graph is in microseconds. So we're going to sample at every 0.5 microseconds on the graph. We are going to start from the leftmost side. So we are going to take a sample at time 0. Which means that we're going to circle the first, or circle all the sample points that we're going to use, and we're going to circle every 0.5 microseconds. So every time we hit that on the graph, it doesn't have anything to do with where the value is on the y-axis for this. We are just circling every 0.5 microseconds to get those sample points. So please do remember, I know a lot of the time, this is a common mistake on this type of problem where people will try to circle like when it crosses the quantization intervals or something like that, but that's not how this works. We're just, a dumb machine that is taking a sample every so many microseconds, and it doesn't matter where that signal is. We're hoping that it's an interesting point to sample. And so that's what we're doing, just sampling every 0.5 microseconds, and that's based off of T equals 1 over F, and F is given by the start of the problem. So then indicate the quantization intervals and the corresponding digital words. So we already kind of did that. We talked about what those bit values would be up here. So more generally speaking, if we have, a 2-bit quantizer, that means we're going to have 2 to the squared intervals, which is 4. So we're going to divide this graph in half to get 2 intervals, right? So anything below and above would be, this would be a 1-bit quantizer. And if we divide each of those intervals in half again, that gives us 1, 2, 3, 4 quantiles. We'll label 0, 0, 0, 1, 1, 0, and 1, 1. And that gives us the same range that I talked about before, which is that, this, sort of 1 to 2 volt range is 1, 1. This, 0 to 1 is 1, 0, so on and so forth. So that's it for part D. And then indicate the digital word assigned to the first 5 sample points. It says assume that your circuitry rounds up when a point falls on the interval boundary. So the first one here, we look at where this point is. We go to the right and see our quantization interval is 1, 1. Here we look again. It is also in the 1, 1 part. Here we're on the line, so it told us to do 1, 0 for that because we round up. Here we're in 0, 1. And then here for our 5th point, we are again on the line, so we're at 1, 0. And that's it. We could continue going. This would be 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, and then 1, 0. So that's how we would label all the rest of the points. So that is it for question 3. Let's move on to question 4 now. So for question 4, it says a receiver for communication system utilizes even parity, receives the following data packet. Any synchronization bits have been removed. Has there been an error in transmission? So even parity means no errors if even number of ones. Right, so we're just going to count. We've got 1, 2, 3, 4, 5, 6. So 6 ones means no error. If it was odd parity, we're looking for an odd number of ones, and that would mean no error. For even parity, if there are an odd number of ones, then that means there was an error. So we're just assuming that we've appended this last bit. So if we asked like what the original data message was here, it would be these first n bits, and then the 1 at the end is the parity bit that we use to make that value, that even parity, work properly, right? So we saw that we had an odd number of ones. We add a 1 to make it even, and that means that it'll detect no error. So that's it for those problems.